My name is Roger. I am a research fellow at the University of Strathclyde. And today I will talk to you about how we use metamaterials to achieve directionally sensitive acoustic sensors. Conventional materials derive their properties from their chemical structure and the arrangement of the atoms within the material, and that's what makes them display or obey the natural laws of optics, acoustics, and mechanics. On the other hand, metamaterials are engineered nanostructures or microstructures or even multi-material structures that enable unconventional manipulation of acoustic waves, mechanical waves, and so on. And that gives them the unconventional properties of negative densities, chiralities, or bulk modulus, such that you can manipulate waves to do what you want them to do. One of the things that we do in our group is to manipulate acoustic waves with the aim of acoustic manipulation to attenuate noise, to attenuate sound. And one of the ways in which we do that is by exploiting Helmholtz resonators, which are essentially bottles. So a Helmholtz resonator, in case that someone is not familiar with them, consists of a neck that then expands to a cavity. And basically that's it. They've been known and very well studied for like 2 centuries. And it's well known that their acoustic properties only rely on their geometry and their morphology and their dimensions. So what we can do is to develop or just calculate the dimensions of these resonators to make, excuse me, to attenuate sound at a certain frequency, and then we can arrange them in this n-by-n structure in order to enhance sound attenuation. As I said before, we're interested in understanding the behavior of these samples or these metamaterials in open air conditions to get more realistic world, live world scenarios. And the setup that we use is extremely simple. As you can see there, we have our metamaterial and microphone set up on a rotating stage that will make sense later. We have our speaker and we have our microphone connected to the preamplifier, and that's it. There's nothing crazy, there's nothing strange, there's nothing difficult. That really is it. The only thing that we do is we run a calibration file before running each experiment, and that's it. If we test them at periodic chirps, we see before the metamaterials nice and flat, and then this metamaterial, these dimensions are calculated to present that center frequency of the bandgap at around 1850 hertz. We'll just call it 2000 hertz. It will also depend on the uncorrection factor that you use. And we see like a very clear 20 dB decrease there. There's a very clear bandgap. And as I said before, there's nothing, I don't want to shoot myself on the foot. There's nothing too interesting on this. This is very well understood for 200 years. If you run your mathematical equations or your simulations, you can get very nice predictions of the acoustic behavior of this. So the question is, if we want to go to lower frequencies, it's a resonating system. So the solution is to increase the volume, but that might not be practical for certain applications. If you wanted to use this as a insulation for a headset, for example, or like anything else that you can imagine. What we do is that we modify the unit cell of our metamaterial and we add a membrane at the bottom. We remove the solid part of the Helmholtz resonator and place a membrane. Everything else remains exactly the same. And you can see there, nice and flat before the metamaterial is there. And after the signal stabilizes, we see that there's a huge shift of the center frequency of the bandgap, and we're moving from 2000 hertz to 600. We also see that there is a very clear change on the bandwidth and the characteristics of the bandgap. You can see it there. And again, if we compare, that's like huge difference. We know after some investigations and some experiments, we know that this shift mainly depends on 3 properties, mechanical properties of the membrane, basically the density, thickness, and the tension. Most importantly, the tension. And we also know, or basically we're moving from a 1-port acoustic system, from a Helmholtz resonator where acoustic waves can only go through the neck, to a 2-port acoustic system where the membrane vibration introduces a non-negligible pressure port there, and that dictates that shift as well. So it's a combination of these mechanical properties with this 2-port system. Seeing this point, like reaching this point here, it's kind of intuitive that this type of system will display some type of directionality. And that's what I'm going to show you next. On top, it's the normal Helmholtz resonator. You will see that there's really no change, big change. And here you will see how this peak disappears as the sample rotates 180 degrees. I want to say that these are videos for visualization when we run, because they still show pretty well what we mean by directionality. When we run the experiments properly for the polar plots with the calibration files that I mentioned before, happy to talk about them later if someone wants to know more. And that's the directionality that we observed in the Helmholtz resonator, omnidirectional, and a cardioid response at the center frequency of the bandgap of the membrane-coupled system. If we look at all the frequencies, we see that we maintain that omnidirectional response for the Helmholtz resonator, and we find that cardioid response here, where the bandwidth of the bandgap is given by the width of the blue region. And as I said before, maybe you're noticing that this frequency is not 600 hertz, that's a different tension. As I say, if we change the tension on the membrane, we get different bandgap characteristics. So the next question was, okay, how or can we make this a sensor by replacing the membrane, just from a membrane, to a piezoelectric component, a PVDF membrane? And I guess that long story short is yes, but with some complications. So we see that at single frequency, this is a 2000 hertz, sorry, because that's the bandgap frequency, center frequency. We see what we would expect in terms of voltage. If we look at the acoustic response of the unit cell, we maintain the main bandgap there, it's quite noisy, at 2000 hertz, but we see that there's nothing below 2000 hertz. Now, that's because when we are adding the PVDF membrane there, it's not really a membrane, it's acting as a plate, and believe it or not, makes a huge difference. And instead of observing undertones, we observe these overtones here, and these are dictated by other physical parameters. We could stop here and chuck this and put it in the bin, or we could still say, okay, well, we can still run the experiments with plates and see if we can detect that energy that's being transmitted, or that energy that's being transmitted in the bandgap. Can we still detect it? Again, well, this being a bit more complicated than it seems, again, quick answer is yes, but with a lot of asterisks that we can discuss later if you want as well. So the next question was, okay, well, can we use 3D printing? The idea behind using 3D printing is to achieve high resolution, to achieve higher control over the geometry, but also over the materials that we can 3D print, and also to do like crazy stuff in the future, like metamaterials, where the membrane could have also a microstructure that would help attenuating more, for example. I don't want to spend a lot of time on this slide because this is not a chemistry conference, but I will try to be like really quick, right? Conventional way that you would do this is you would get your piezoelectric filler, nanocomposite, nanoparticle, nano whatever, nanorod, whatever it is, PZT, barium tight, whatever, and you would take a photocurable resin, you would mix them, and you would print it. Problem is that you lose resolution because the light, the particles scatter the light, and then you have this kind of membrane around your sample. You can fix that by adding what's called a photo blocker that has this orange tint, and then you can see that the resolution is incredibly nice. The problem is that your piezoelectric constant, your DC3 goes down, so you need to find a trade-off, and then that's, well, if you want to develop a sensor, you need to decide if you want like better resolution or better sensitivity. So one of the big points here was to develop a filler-free photoresponsive piezoelectric resin that would provide higher piezoelectric values. You can see that in this one, there's still a bit of light dispersion. This is filler-free. Happy to discuss this later if someone has any questions. This is not chemistry. If someone's interested in the chemical process, that's it. But again, main story being that we can develop different types of 3D printable PVDF-based composites. If we go back to sensing, bad news is that this still does not behave as a membrane. Good news is that we can detect that directionality pattern. So we have two main bandgaps there at 180 degrees, setting this up with this material, and we can get detection peaks corresponding to energy being transferred at these bandgaps. Again, there's a few asterisks here, happy to discuss later. But as I say, we can still detect that directionality at a much lower sensitivity, of course, because our D33 is much lower than commercially available PVDF. We are now at the point of trying to have a better understanding of the full system as a whole. And we are at a point that we want to get a full picture of simultaneously what's going on. So what is the electrical signal, what's the membrane vibration, what is the acoustic response of the system while we rotate the speaker around the full system. We're trying also to match the resonance of the membrane with the band gap in order to get higher voltages out of it. And we're trying to detect multiple peaks at the same time. But as I said, this just turned out to be like more complex than we thought it would be like really, like not really straightforward, but much easier than it ended up being. Long story short, you see again different shapes, very high uncertainties at higher frequencies, kind of correlatable peaks there. 90 degrees, we have two kind of peaks there, and 180 degrees, the response is completely different again. But that can be a combination that we still are investigating of all these interactions combined with the membrane resonance itself there. That it can also be contributing. I will just finish up. I don't know if I'm on time or not. So I'll just conclude by saying that we managed to reduce, or we can indeed reduce the band gap center frequency of the band gap by keeping the same resonator size and simply by modifying the unit cell by introducing a membrane. And that the membrane characteristics together with these two-port system dictate that shift and the characteristics of the band gap. We indeed obtain directional response. Now, if we wanted to hide something, that might not be the best result, because if we want to hide something at these blue regions, well, if you have a region that's amplifying sound just before, it might not be very clever. But we just want to detect sound, so I guess it works for the time being, and we will just deal with this later. Introducing a functional membrane, I keep saying membrane, but it really is a plate, enables detection, seems to enable detection of energy being transmitted in the band gaps, and we can achieve similar results through 3D printing, different functional PVDF materials, but with limitations and with a lot of things that we still need to fully understand to get a better picture of what really is going on here. I would like to finish just by thanking everybody in Kew and at the University of Glasgow in the collaborations. I will be more than happy to answer any questions or have a chat after, so thank you very much.